Hello and welcome back to the 4.2 notes. This is a video over the second derivative test. We learned about the first derivative test, but the things that I want to talk about that that the second derivative test allows us to do is this. So I'm going to come in here and I'm going to write the second. Let me change my font. Okay, so we have the second derivative test. Okay, derivative test. And this allows us to check for concavity, okay? So it allows us to check for concavity and allows us to find points of inflection, okay? Points of inflection. Okay, so the first thing I want to talk about is concavity. And concavity is an interesting thing that we talk about. But the first thing I want to talk about is something that's concave up. Okay, concave up. And it's a graph that opens up. Okay, concave up is really just a graph that opens up. So I'm going to say graph that opens up. Okay, and we've kind of talked about this for a long time. The one example that I can give you is the equation y equals x squared. Okay, when we would say the parabola opens up, okay, this is y equals x squared, and this is an example of something that's concave up. Okay, all right. The other thing that we can say, the other option is concave down. Okay, and so if I say concave down, then that's a graph that opens down. Okay, so it's a graph that opens down. Okay, and so the example that we have would be, like y equals negative x squared. Okay, and we'll just pretend that that is a good-looking graph. Okay, with arrows, and I'm going to call this y equals negative x squared. Okay, and so these are just the examples of concave up and concave down. Okay, so and then let's quickly talk about a point of inflection. Okay, and a point of inflection is when concavity changes. Okay. All right, and that's what we're going to do. So the one thing I do want to talk about here is how do we get these things? How are we able to come in here and to know when something is concave up and something is concave down? So I do want to go back to that problem that we've been talking about for all year long, where we throw an object in the air. Okay, throw the object in the air, it reaches a maximum height, and then it falls to the ground. Okay, we know that the object slows down, okay, as it's reaching its maximum height, and then it starts to speed up. Okay, and this is our position function. Okay, this is our position, and this is also, we can also call this f of x. Okay, function f. Okay, and then if we take the derivative of that, and we call this f prime, okay, the derivative, this is also our velocity function, okay? And what we know is that the object speeds or slows down, okay, when it has a maximum height, the velocity is 0, and then the velocity turns negative because the object is going down, and the object speeds up, okay? Now, this is all due to what we call acceleration. Okay, if we take the derivative of our velocity, then we get acceleration. And this is our second derivative, okay? Now, what I want you to know here is that, we have a constant of, our constant acceleration due to gravity is negative 9.8 meters per second squared, okay? And so when we do that, when we have that, the value of my second derivative is negative, okay? Now, I do want to say that. I do want to say that f double prime is less than 0, okay? Meaning that f double prime here is negative, all right? And so what we notice from that, because my second derivative is negative, we want to look at the shape of our position function, and this is a parabola. and this parabola opens down, okay? So we could say that this function here, okay, is concave down. Okay, so we know that this is concave down, all right? And so, the conclusion that we can draw here is that we are concave down, all right? And let me come in here and write that, all right? We're concave down, all right, if f double prime of x is less than 0, okay, then we know that f of x is concave down. And I'm going to use that notation here, concave down. Okay, this means concave down. All right, so, the other thing that I do want us to notice is that our function, because our second derivative is negative, then we also know that f prime of x, f prime, is decreasing. Okay, so because f prime is decreasing, okay, that's a result of f double prime being negative, okay, and that's the first derivative test. Okay, so I can also say this: if we know, okay, if f prime of x is decreasing, okay, then I can say that f of x is also concave down. So there's two different ways for us to say that something is concave down, okay? And that's just something that we see for this particular example. Okay, now if we were to talk about something that's concave up, all right, so I'm going to do that over here. I'm going to call something that's concave up. Then I do want to talk about this. All right, I do want to say that it's the opposite. Okay, if we come in here and we say that, say if f double prime of x is greater than 0, okay, if our second derivative is positive, then we can say that f of x is concave up. Okay, meaning it opens up. All right, so, and let me go ahead and do that. Let me say this, okay, if we know that f prime of x is increasing, okay, then we also know that f of x is concave up. So we've got two different tests here, okay? We know that f of x is concave up as well, okay? So what I actually want to do here is I actually do want to go through the second derivative test on this, okay? And I do want to show you like what we would do here for this example. So I do want to do the second derivative test. All right, so if I do the second derivative test, all right, we do the same type of thing. We make our interval, okay, we do our sine of f double prime, and then we talk about concavity. Okay, and I'm going to do this a bunch of times, so if right now, if it doesn't really make sense, that's okay. But what I do also want to talk about here is, and really what the second derivative test allows us to do is find points of inflection, okay? And that's kind of what we're concerned about, but it also tells us where we're concave up and concave down. And so we do a similar type of thing if we're trying to find critical points. So critical points here is when f double prime of x is equal to 0, okay? And so on this example, our graph does not, our acceleration is constant, so it's not actually going to hit, the x-axis. So we do not have any critical points. So we have no critical points here. All right, and so our interval that we're talking about here is just from negative infinity to positive infinity, okay? And we know that the sign of our second derivative in this example is negative, okay? We know that it's below the x-axis. We know it's way down here. So because of that, I'm going to come in here and say that my second derivative is negative. Okay? And because of that, I know that our function f is going to be concave down, okay, over that interval. All right, and that's true for this entire graph. My entire graph here is concave down, okay? And that's a result of my second derivative being negative. So if you're trying to figure out, okay, how do I know if something is concave down or concave up? Go back to this picture. Okay, and that's the reason why I'm doing this, is because you can go back and you can say, all right, well, I know that my second derivative is always negative for this example due to gravity, and then I know that my graph is going to look like this when I throw an object in the air, okay? And so that helps me know that, okay, because my second derivative is negative, we're concave down. Then the opposite works. If my second derivative is positive, then I know that my function is concave up. Okay, so I hope this makes a little bit of sense to you. I hope this kind of clears a few things up as far as what concavity is. We are going to talk more in depth as to what, how to do the second derivative test and all that stuff that it tells us, and we're going to, continue doing that. So I'm going to go ahead and stop this video. Hope you enjoyed this. Please fill out the notes, and we'll look out for the next video. Thanks. Bye.